TW806, reduce speed to 200 knots, Paris weather, wind 160 degrees, 5 knots, visibility decimal 5 kilometers, runway visual range 460 meters, fog, measured 100 overcast, altimeter QNH 1007 decimal 5.
TWA 806, reducing to 200, weather received, altimeter QNH 1007 decimal 5.
Of all the stages in an aircraft's journey, the most critical is the landing. For a proper landing, the aircraft must approach along a precise path at precise rates of descent and speed in order to arrive over the runway at a point from where a landing may be safely completed. Electronic navigation aids often help the pilot in making his approach, but he must also be able to see the runway before touchdown. It is to provide the pilot with information on visibility and other important weather elements that most airports have weather observation stations manned by trained meteorological observers. Meteorology, the science of weather, has a long history. Long before meteorological services were established, people observed the weather and forecast its trends. This Tower of the Winds was erected 3,000 years ago in ancient Greece and served as a weather observation point. Even today, observing the weather by eye is still useful, but instruments and automation are gradually replacing many of the older techniques which depended on subjective interpretation. Today's meteorological observer has at his disposal a wide range of techniques which enable him to provide the pilot with the detailed and timely information he needs to bring his aircraft safely in for a landing. In the Met Report for pilots, the observer gives information on the following: wind, visibility, including runway visual range if required, weather, cloud, temperatures, dew point, pressure, and, if necessary, some supplementary details. Let us now take a closer look at why the pilot needs to know all this and how the observer gets the information for his report. The first element in the report is the wind, its direction and speed. As a rule, pilots prefer to land into the wind, but sometimes landings have to be made with a strong crosswind component due to the direction of the runway. Here, a light aircraft is landing with a very strong and gusty crosswind component. The buffeting of this small aircraft is a good example of why it is imperative that the pilot be given accurate wind speed and direction, including information on wind variations, in order to be able to take it into account and to land safely. To measure wind speed, the observer uses an anemometer. Wind direction is measured by a wind vane. Both instruments are usually mounted together 6 to 10 meters above the ground and are erected in a location providing representative values of wind direction and wind speed along the runway. Where several runways are available, there may be a need for more than one set of wind instruments. The readout instruments for wind in the observer's office are also grouped together. For aviation purposes, wind speed and wind direction should be averaged over a period of about 2 minutes. Wind direction is reported to the nearest 10 degrees, and wind speed is reported in knots. Variability of the wind, sometimes called gustiness, is also of importance to the pilot. Any variation in direction exceeding 60 degrees and any variation in speed greater than 10 knots must be reported. Frequently, a recorder connected to the readout instruments provides a continuous graph of these wind variations. The wind direction is measured in degrees in relation to true north, that is, the direction of the geographical North Pole. Runway directions are given in relation to magnetic north, and the pilot needs to know the wind direction as it relates to the runway heading. The wind direction is therefore converted to degrees magnetic before it is passed on to the pilot. In order to make the wind information promptly available to air traffic controllers for immediate transmission to a landing aircraft, most control towers have their own readout instruments to save relay time. Another important element the pilot needs to know is horizontal visibility. This is the distance an observer can see horizontally. Visibility can vary from more than 50 kilometers in clear weather to almost zero in fog. When the visibility falls below 10 kilometers, it becomes of critical importance to the pilot. This feature of the Met report is of particular importance because regulations stipulate certain minimum visibility values for landing. This information is available to the pilot from the approach chart of the airport of his destination. Correct appraisal of visibility is very important. If the meteorological observer overestimates the visibility, he may be reporting conditions that are allowing the pilot to fly below the limits and possibly place him in an unsafe position. On the other hand, if he underestimates the visibility, for example, to a value below the limits set, when in fact it is above these limits, he may prevent pilots from attempting to land and be responsible for needlessly diverting aircraft. Diversions not only cause inconvenience to passengers, but also place extra and heavy expenses upon the airlines, who have found that such diversions may cause considerable disruption of their entire operations. One method of determining the visibility is by observing objects, landmarks, or lights at known distances and reporting in increments of kilometers. If it is less than 5 kilometers, visibility is reported in increments of 100 meters. In cases where visibility differs according to direction, the observer must report the different values. In low visibility operations, as the aircraft approaches the runway, the pilot must be assured that on touchdown he will be able to see the runway lights or markers for a range of at least 800 meters. Where electronic guidance facilities are available, this minimum range may be lower. Under low visibility conditions, additional observations are required, applying directly to the runway and the associated visual aids. This is not normal visibility as seen by an observer on the ground, but an assessment of the distance at which it is expected that the runway lights or markers would be visible to the pilot at touchdown. This is called runway visual range, RVR, and is reported at most large airports whenever the visibility is less than 1,500 meters. A transmissometer, one of the instruments used for this purpose, measures the reduction in the intensity of a light beam, and these measurements are then converted into RVR values. At many airports, RVR is automatically determined by such instruments. Because visibility is often variable, RVR should be assessed continuously, and if necessary, at more than one point along each runway, in order to provide the pilot with an accurate representation of the visual range conditions on the runway. Transmissometers are sited alongside the runway and as close as the regulations will allow to provide accurate information on visual range conditions existing for landing aircraft. In the observation station, the transmissometer readings are converted into values of RVR, and a recording device connected to the transmissometer readout again provides a record of any changes in visual range. Significant changes in RVR are transmitted to the control tower for immediate relay to pilots. However, many control towers have a direct readout of runway visual range available. The next item to be reported is the weather. Weather is a meteorological term used for the following phenomena, the symbols of which are shown here. In addition to these weather elements, there are others, such as funnel clouds, tornadoes, or ice pellets. A variety of terms are used with these weather descriptions to indicate important qualities, such as freezing, patches, shallow, or blowing. The pilot is also interested in clouds in the vicinity of the airport, as these clouds may be associated with atmospheric turbulence or thunderstorms in the approach area. He is primarily concerned with the amount of cloud and the height of the cloud base. The observer estimates the amount of each cloud layer in eighths or octas of coverage of the entire sky. This particular layer of cloud covers half of the sky and is reported as 4/8 coverage or 4 octas. He then estimates the height of the cloud base above the airport by reference to nearby hills and other landmarks, or he measures it by means of instruments. Here is a rotating beam ceilometer, an instrument which is installed at many airports for measuring cloud base. It is usually located near the middle marker of the instrument landing system, that is, about 1,000 meters from the runway threshold on the approach. This instrument projects a beam of light toward the sky. The ceilometer provides a very effective method of accurately detecting the height of cloud layers, even in daylight. The detector, located some distance away, picks up the beam at the point where it is reflected by cloud. In the observer's office, cloud height is indicated by means of readout instruments. On the screen of this cathode ray tube, the cloud base can be continuously monitored. A ceilometer recorder keeps a faithful record of cloud conditions over a given period of time. The recorder is read at regular intervals, and cloud height measurements are then entered into the Met report and conveyed to the air traffic control tower. A more simple method which provides useful measurement at night is by directing a searchlight, known as a ceiling projector, vertically at the clouds. Then, by sighting the illuminated spot on the cloud, the height of the cloud base can be established by triangulation. This sighting device is known as an alidade. Still another method of determining the height of the cloud base is to release a small gas-filled balloon inflated to rise with a known rate of ascent. The height of the cloud base can be determined by noting the time it takes for the balloon to disappear into the cloud. This also serves to indicate vertical visibility. For landing, pilots are especially interested in the height of the base of the lowest clouds, when it is less than 1,000 meters above the height of the highest obstacle in the approach area. Therefore, in Met reports for landing operations, information about higher clouds is not usually given. Cumulonimbus clouds, however, particularly when they occur in the approach area, are always given. Their presence is significant for the pilot, as they may indicate turbulence or thunderstorms. Temperature and dew point measurements are also included in the Met report for landing aircraft. They are given to the pilot only when requested and provide him with an indication of the relative humidity, that is, the degree of saturation of the air. Freezing temperatures at ground level should alert him to the danger of aircraft or engine icing. When the difference between the air temperature and the dew point is small, and the spread between them decreases with successive observations, the likelihood of fog increases. This information is useful to a pilot when he is deciding whether to hold for an improvement in visibility or to divert to an alternate airport. Air temperature is more important for takeoff than for landing, for as air temperature increases, the density of the air is reduced. The lower density of the air makes longer takeoff runs or lower takeoff weights necessary. Air temperature and dew point are usually measured with the aid of thermometers installed in an instrument shelter to shield the instruments from direct sunlight. A wet bulb and a dry bulb thermometer are mounted together. The wet bulb thermometer is kept moist by means of a wick immersed in clean water. The thermometers can be read either directly or, where remote readings of wet and dry bulb thermometers are available, the observer determines air temperature and dew point in his office. Here is a fully automatic hygrothermometer, which furnishes a direct readout of ambient temperature and dew point without the necessity of making calculations. This equipment provides accurate readings with a high degree of reliability and requires very little maintenance. Another important element which makes up a weather report used in landing operations is pressure. The pilot's altimeter is a pressure-sensitive instrument and will provide a correct reading of aircraft height above the ground only when it is set to the proper pressure reference. ICAO standards require pressure to be reported in millibars. The observer determines the atmospheric pressure by using a barometer. There are two types of barometers in common use. This is a recording type aneroid barometer, and this is a mercury barometer. Pressure is read at regular intervals, and readings are converted into pressure values for altimeter setting purposes. Conversion is accomplished by using standard calibration curves. This type of pressure reference is called a QNH, and if the pilot sets his altimeter to this reference, it will read on touchdown official airport elevation plus the distance from the wheels to the instrument. Another type of pressure reference used is the QFE. This pressure is not reduced to sea level, but is converted to airport elevation, so that the pilot's altimeter will indicate height of the instrument above airport elevation if he has set his altimeter to the QFE value. Clear distinction should be made between QNH, for which the pressure datum is mean sea level, and QFE, for which the pressure datum is runway elevation. The Met report for local airport distribution is usually in abbreviated plain language. Distribution may be by this electromechanical writing device, or even by closed-circuit television. Here, the weather report comes off the electromechanical writer and is put in front of the air traffic controllers for immediate transmission to pilots. During extreme meteorological conditions, such as thunderstorms or snowstorms, the reporting frequency is increased. The aviation weather report may also be expressed in a coded message form called METAR. This direct reading report is designed for transmission over communications circuits to airports around the world and may also be used for other than aviation purposes in accordance with procedures developed by the World Meteorological Organization. These, then, are the main features of a meteorological observer's report for landing aircraft: wind, visibility, weather, cloud, temperature, dew point, and pressure. Finally, other information such as vertical wind shear or cumulonimbus clouds in the approach area, mountains or hills being obscured, or variations on visibility should be given when significant. This additional information is to provide the pilot with a full picture of meteorological conditions and to supplement the standard elements in the Met report. For example, vertical wind shear information